Thank you, everyone, and good afternoon, everyone. I am David from the Hong Kong University of Science and Technology, and I am also a recently Master of Philosophy student under the supervision of the Hong Kong Center for Construction Robotics. And actually, it is very pleasure to present after two kinds of these famous professors. And in the coming minutes, I will share some of my findings on controlling the tower crane systems. So during the current year, it has been found that the modular integrated construction is more and more widely used. But however, it brings some challenges on installation and the transportation. And for those payloads which have tons of mass, tower crane systems are all usually used to in the construction sites to move the MICs. And before going into the solving part, it needs to be firstly identified what is our goal when conducting these kinds of transportations. We need to move the models to the desired position. One important requirement is that we need to move it stably. Besides, the key point is that the end-state swing angles need to be well controlled to do the installation later. And nowadays, two kinds of different classic control approaches are firstly the input shaping open loop methods. These kind of methods are kind of feed-forward controls to make comments to the actuators during the progress. And well, the effect is only considered based on the end state. And on the other hand, the feedback compensation method are based on the sense signals. And they will always try to make sure the status of the system to follow the reference of the controller. And the open loop methods are not robust enough to the external disturbances. And for the closed loop ones relies too much on the feedback signals. Hence, this paper is trying to make a balance between these two kinds of methods on controlling tower crane system. So then we start our solution part. First of all, we need to use the tower crane system to model and find our dynamics equation, which are related to the control elements and also the input. And just like what are shown here, there are two relative dynamic equations controlling the two swing angles. And we use a time polynomial function to feed the input signal as our methodology. So the key mathematics principle for this paper is that if there is a polynomial form, just like showed here, and we want it to be zero for whatever the time is, the only way is keep all the coefficients to be zero. And on the other hand, based on the Laplace transform principle, if the trolley position is set as the time polynomial form, like here, it will be obvious that the left side of the two dynamic equations will be also time polynomial form. So with the input coefficients, we can express the two swing angles. And then the control objectives are introduced to determine how to solve the coefficients of the trolley. And the control objectives are shown here as both the initial states and the end states we need to consider. And we consider the jerks, accelerations, velocities, and the positions of the trolley. And also we consider the swing angles values and the angular velocities to make it just stable at the initial at the desired state. And the TF here is the transportation time, and we will find the smallest value of it to find the optimized motor input. And so the above part has shown the open loop characteristics of the proposed method. And the influence of the external disturbances needs to be resisted by the feedback loop. So given the initial position and the desired position, the open loop command generator could calculate out the time polynomial function of the both the trolley position and the swing angles, and these will be used as the reference in the feedback loop. Next, so in this paper, we want to test the performance of the on a real size scenario. So, well, it is quite difficult to do experiments at the beginning level. So we conducted the simulation firstly. And the first condition is used to test the reliability of the polynomial fitting method. And just like the example here, the input acceleration changed smoothly to make the trolley reach the desired position. And also, in addition, the end state angles are controlled at the same time the trolley reaches the desired position. So next, under another condition with some external disturbances, the proposed method is tested with the some closed loop comparison methods, and we can find that the end state angles are controlled quickly as the green lines, and the comparison method needs more time to make the angles convergence. So besides, for positioning performance, there is no obvious overshoot for the proposed method with the positional changing. And we can see that the input of the proposed method is much smoother than for the motors to check. And there are too many oscillations for the input for the comparison controllers. And actually, it is very hard for the motors to execute. So to conclude, the proposed method considers the actuator operation limitations and completes the positioning missions, controls the end state swing angles, and also shows the robustness to the external disturbances. So we can say that this is one of the composite control methods, and it has a relatively good performance. So in addition, the method also has some potential future directions on controlling the real-size tower systems. We are recently working on enlarging the degree of freedoms of the tower system with the 2 or above inputs coordination. The tower system will be able to avoid the obstacles. And since the inputs are very obvious to be the polynomial form, so we are also trying to find the coefficients with some AI tools. And here for some extension, actually, before preparing this PowerPoint, the performance of the 2 degree of freedom tower crane system has been already verified. And you can see, actually, we have 4 angles here, and all the 4 swing angles are well controlled by the proposed method at the end stage. And both the trolley position and G rotation angle reaches the desired state accurately. So that's all for today's presentation, and thank you for listening. I think there will be a QA later, and I appreciate for your question. Thank you.